Okay. So my talk's going to be about using semantic testing framework to find bugs in the Solidity compiler. A brief note of introduction. I'm a security engineer in the Solidity team at the Ethereum Foundation. And most of my work involves, like I said, using semantic testing tools to find security critical bugs in the compiler before it is shipped to end users. For those of you who are getting a bit impatient already, this is a brief summary of my work or the talk that I'm going to present. Before we set out to find security bugs in a piece of code, we need to define a threat model. In other words, what is the class of bugs that we are interested in and what threat it poses. So for us, the threat or the class of bugs that we're interested in finding out are those that lead to incorrect code generation. And this is exactly the class of bugs that we want to find before a compiler is shipped to end users. And the approach we use is a form of semantic fuzzing, which is based on a specification. So we randomly generate programs based on a handwritten specification and use this to get an assurance that most of the optimization against randomly generated test programs is done correctly. And if it's not done correctly, then we have an example use case where optimization is done incorrectly, and that we flag as a bug for future investigation. Now, this approach has been quite useful in practice. So far, we've found about 9 bugs using this approach in the Solidity optimizer, all of which have been, of course, patched by now. And inspired by the success, we continue to use this approach on a daily basis in a service that is called as continuous fuzzing. So essentially, every day, Solidity code is tested continuously so that as soon as we find a bug, we come to know about it and we fix it as soon as we find it. So let's get started. As I mentioned in one of the earlier slides, it's important to start with the threat model. And our threat model is the class of bugs which demonstrate a bug in the optimizer. By which I mean, let's say you have a program which after optimization behaves differently than before it was optimized, which means that perhaps optimization was not done right. What we clearly exclude in this threat model, at least for the class of bugs we call security critical, are bugs which do not expose a bug in the optimizer. In other words, we explicitly don't consider the compiler user or the programmer to be malicious, and we exclude the class of bugs which result in benign compiler crashes. This slide is mostly intended for people who are unfamiliar with fuzz testing. So I'm going to give you a brief introduction. In a nutshell, fuzz testing means essentially in an iterative way, in a continuous loop, generating random test input for a program under test. And essentially, this process completes either when you've found a bug or you've not found a bug, but you're fairly satisfied that the input space that has been explored so far by the fuzzer gives you some assurance to go ahead and ship the software. So it's somewhat arbitrary, but it's actually quite useful in practice. And traditionally, fuzz testing has been as simple as it sounds, it's been pretty successful in finding some interesting corner cases in a vast variety of software. Now, I said that it's actually quite useful, but done in the naive way, randomly generating test inputs, is not very useful to test programs such as the compiler. And the reason for this is that, let's say we start with a program that is shown on the left side, which is Solidity pseudocode, and let's assume that it's syntactically well-formed. And let's say the fuzzer generates a random mutation which results in the program shown on the right. And you can clearly see that we are quite likely to end up with a mutation in which the fuzzer has essentially turned some essential keywords into garbage. In this case, the keyword function and the keyword public. And what this does is that it makes the test input unparsable. And this is a problem to test the optimizer because it's right away rejected by the Solidity parser. So what we require is an approach that preserves the syntax of the target language. And not only that, in the best case, it also introduces interesting language constructs that explore different parts of the optimizer. I'm going to describe how we do this in the following slides. So, so far what we know is that the naive approach of fuzzing, which is to generate random test input, is not very useful to test a program such as the compiler, whose input is actually structurally well formed. So we need an approach which takes this structure awareness into account. So let me get started with how we do this. Our approach comprises 3 steps. In step 1, we write a manual specification of the target language under test. In this case, it's actually YUL. YUL is an intermediate language used by the Solidity compiler for optimization purposes. So what this specification looks like is shown in the slide deck. We use the protobuf interface description language developed at Google to write such a specification. And the fundamental unit of description in protobuf language is something called a message. So we can use this to define the syntax or the grammar of YUL in a bottom-up manner in such a way that we can define a block or a basic block to be a sequence of statements, and upwards a program as a sequence of basic blocks. Of course, I've left out a lot of different constructs to make it easier to comprehend, but if you're interested, I've linked the full specification below. So we use the protobuf interface description language to define what YUL syntax looks like. And in step 2, what we do is we employ a library called the libprotobuf mutator. This has also been developed at Google. And what libprotobuf mutator does is it accepts a protobuf specification and essentially generates random variants of messages that conform to the specification. So you can think of it as a random generator of the specification that you write. In the end, each input that the libprotobuf mutator generates is a tree. And in text form, it looks vaguely like JSON and is shown in the slide below. It's not important to understand what this encodes because I'm going to describe it briefly in the next slide deck. In step 3, what we do is we convert this protobuf message into a valid YUL program. Of course, this is necessary because we are ultimately testing the YUL optimizer, so it does not understand anything other than the YUL language. So we write a simple program called the converter, which accepts a valid protobuf message and converts it into a YUL program. So using these 3 steps, we can, in the end, generate valid YUL programs that can be used as test inputs for the optimizer. So to give you an example, I have tried to show what it looks like when a valid code snippet from the protobuf interface description language is converted into YUL. So essentially, the protobuf protobuf input consists of a block of statements, and the statement consists of an if statement whose condition is a binary operation, which is an equality operation of a variable reference, assuming that the variable has been previously declared, and the constant 0. So essentially, this converts to the YUL snippets shown at the bottom. Of course, this is a very simple example, and already the protobuf language has made it a little more verbose. But in practice, we have longer sequences of such protobuf messages that we use to essentially encode a full-blown valid EUL program. So in summary, the workflow looks like this. We start with the manually written protobuf specification shown on the left. We use the libprotobuf and libprotobuf mutator libraries to generate various messages based on the spec. We use a converter to convert these messages into valid EUL programs, and finally use these test programs to test the optimizer and see if there's a bug or not. So far, I've spoken about test input generation, but actually, we need an oracle to decide whether there is a bug in the optimizer or not. So how do we decide whether there's a bug? For this, we use an approach called differential fuzzing, which comprises 4 steps. First, we track side effects of execution of an arbitrary EUL program. I'm going to describe this briefly in the next slides. In the next 2 steps, what we do is first we run the program that has been generated by the fuzzer and subsequently converted and obtain an execution trace of this program. And second, we optimize the same program and rerun it again and obtain another execution trace. In the final step, we compare the execution traces or side effects of these 2 sets of programs. Now, since side effects encapsulate semantic properties of a program, they have to be the same if we are executing the same program. So whether it's optimized or unoptimized, the side effect has to be the same. So we can conclude that if the side effect of the 2 sets of programs is different, then it's most likely that there's a bug in the optimizer. So now I describe how we obtain a execution trace of an arbitrary EUL program. For this, we depend on the EUL interpreter, which essentially interprets an arbitrary EUL program and outputs the side effect of the input EUL program as a trace or a string. So it looks like so. On the left, it takes a EUL test program as input and outputs an execution trace. The execution trace holds the side effect of the program that was executed. It contains the sequence of EUL instructions that were executed and the side effects they had on storage and memory. So putting all of this together, our fuzzing setup looks like so. We use a protobuf-based program generator, and we use a converter to convert this into EUL. Each program that is randomly generated is then fed to the interpreter as is, and also fed via the optimizer. And these 2 programs are then compared to see if they have the same side effects. In most cases, they should, but in very rare cases, it's possible that they don't. And when they don't, it's quite likely that it's because of a bug in the optimizer. And that's how we flag issues for further investigation. More recently, we've been experimenting with an additional plugin to improvise on the program generator. To recap, I mentioned that we use libprotobuf to generate programs, but recently we found that randomly generated programs may miss certain customizations that are required to test specific portions of the optimizer. For example, with what probability a certain construct is inserted or not. So to make use of these customizations, we've started to write a small plugin to improve on the program generator. For example, one simple custom mutation could be negation of a Boolean condition in a branch statement. So for example, let's assume that a small snippet of the code generated by the program generator is if x0 equals 0. The custom mutation could then be mutate such a program such that the Boolean condition is negated. And this turns the test program from the one shown on the left at the bottom to the one shown on the right with the if condition flipped. Now, this is a very simple example, but in practice, it's often necessary to have mutations that essentially insert those UL statements that cause difference in program control flow. So for example, in adding UL statements such as break, continue, return, or leave, such as these statements is often necessary to test various portions of the optimizer. So using this approach, like I said, we found about 9 bugs so far. 7 of them have been in the UL optimizer and 2 in the optimization rule, if we were to break down which component is affected. But fortunately, the majority of these bugs were found when the UL optimizer was still in an experimental phase. So they did not affect production programs. But in any case, we were very quick to release patches so that the impact on end users is minimized. Also, another observation is that most of these bugs, if you were to classify them according to security severity level, most of them have low or very low severity. And the reason for this is that they either can be already found during smart contract testing because they're simple enough to be flagged, or that they require multiple prerequisites to be satisfied for the bug to manifest. And in most of these cases, we find that the set of conditions that need to be satisfied for the bug to actually manifest itself is actually quite far-fetched in practice. That's why most of them are low severity. Of course, I spoke about custom mutations, and one success we've had with these custom mutations is that a medium severity bug was actually found, and this goes to show that customizations can always help. So this brings me to the end of the talk. In summary, I presented to you the approach we're using called continuous structure-aware fuzzing to test Solidity and its optimizer on a daily basis. I mean, of course, the end goal is to find bugs very early, and of course, that'll help us fix them early as well. And this has been particularly useful to test the optimizer and, of course, data and in decoding, which I didn't speak much about because most of the talk was focused on the optimizer. Our experience has been that this provides a decent assurance that the code has been well tested. Of course, we have evidence that it works or it doesn't, because if you have a failing test case, this can be immediately flagged for further investigation. But we need to bear in mind that testing does not provide formal guarantees. So this makes it important to continue the investigation on what can be done to essentially improve test coverage on the one hand, or the likelihood that certain components of the optimizer are well tested, which is what we've started to do recently. Thank you for your attention, and I hope you had the opportunity to attend my colleagues' talks, which were yesterday and today. If not, you can always watch the video.
Have you some question? Yeah.
Hi, do you see any false positives or false negatives down the line when you are doing fuzzing, and how do you deal with that if so?
False positives are relatively easy because you can reasonably quickly determine whether, because you have an input test case which you can debug, you can quickly determine whether it was the optimizer which is the root cause or some shortcoming in the fuzzing setup. False negatives are harder But of course, we need to bear in mind that in general, testing will have false negatives. So the way we deal with false negatives is essentially on a manual investigation basis to check if test coverage is sufficient, if all code paths are being covered, or to essentially experiment a bit with the kind of test inputs that are generated. If certain classes of inputs are missing, so what can we do in the fuzzer to generate these inputs? So it's a much more harder problem to solve. Yeah.
Thanks.
Yeah. First, thank you for your presentation. A question which is maybe hypothetical, but still interesting. So, how many low-level optimizations you have in the compiler? Is it possible for someone to include some security vulnerability on purpose for some member of the compiler team in order for the thing to be, stealing some money or whatever? So, are there places in the compiler where only few people understand, or some optimizations that are done by hand?
So are there places in the compiler a few people understand? We are a team of, I think, 9 people or 10 people. I don't know. So yeah, I believe we have contributors from outside, so it's hard to define how many people understand. But I think in general, for any piece of software, you could have an insider essentially introduce a bug. I think there was a paper by, I forget the name of the author, in the 70s, which showed that a cleverly designed compiler could introduce bugs. But of course, I mean, that's not our purpose. Our aim is, the reason we are doing this is actually to find bugs soon. So for us, the more interesting threat is accidentally introduce bugs causing problems. So yeah.
You use random generation to find bugs. Is it new random things every time, or is it random once and then the same random thing over and over again every day?
It's random every time.
Okay. Then how long do you let it run before considering, okay, there is no bug when you enter a new features in the compiler?
I believe we don't have a precise definition for how long to run, but the service that we use is called Google OSS Fuzz, and that runs every day for at least a few hours. So if something has not been found for a few hours, it is likely we miss it. But in practice, it's been quite unlikely. It either finds it very fast or something is missing and we need to do extra work, like I mentioned, the customization feature to actually find a bug. Usually I feel that a few hours of fuzzing with a good set of inputs that has been accumulated over time, it's sufficient. Also bear in mind that the so-called test input is a cumulative accumulation. So if we start from day 0, and let's say we enrolled this project over 2 months ago, so we have accumulated 60 days of inputs. So it keeps getting better and better, hopefully. So it makes it easier to find new bugs. But having said that, like I said, it is possible that the fuzzer itself has blind spots. So it's important to customize it from time to time.
Thank you.
Great talk, Bhargava. Thank you. I was wondering whether you benched libprop of Mutator and or libfuzzer against other fuzzers. So have you looked at honk fuzz? Have you played with? I think Google released a few days ago Fuzzbench that allows you to basically use your OSS fuzz project and bench it against whole sorts of different fuzzes. I'm just trying to understand if you guys have done your sort of benchmarking to pick up a particular technology, if that makes sense.
No, we've not done that. I saw the project recently. It would be definitely interesting to do that. Just to know if we are missing something that some other fuzzer can catch. So as far as I understand, we need to somehow convince Google to add Solidity to their benchmark so that we could use it, or maybe we can tweak it ourselves. But it'll be definitely an interesting experiment to see if we are missing something. Yeah, thanks for that.
Any other question? No? Well, thank you very much.